I will be talking about robots that can anticipate and adapt to change. And like the title of the workshop, we're specifically going to talk about how we can design learning algorithms that can operate in dynamic open world environments. And the algorithms will be relevant to things ranging from legged robots to autonomous vehicles to robot manipulation. So what is actually meant by a dynamic environment? So I want to start by giving a concrete example to start thinking about these challenges. And in particular, let's look at an example from robotic manipulation, where we develop a grasping system that can learn how to grasp with reinforcement learning to a success rate of 86%. Now, if something changes about the environment, for example, there are harsh lighting conditions, maybe the robot encounters new objects like these transparent bottles, or maybe a checkerboard background, or maybe even something changed about its morphology, like the gripper was offset by 10 centimeters. What we find is that if we take the policy that was learned in the training environment and deploy it in these settings that are a little bit different, the performance drops drastically from 86% down to 30 to 50% success. And so these are all relevant kind of changes or settings that we want robots to be able to handle. How might we actually go about mitigating this and allowing the robot to handle these different environments? Now, of course, one really simple idea here is, how about we just use fine-tuning? Instead of just deploying a static Q function, what we can do is we can continue to learn using experience from the new environment. And so in particular, what I mean is our base Q function, or our base policy, was trained with the QT-opt algorithm to get 86% success rate in the training environment. But when the robot is in a new environment, and in this case, getting 43% success, it doesn't need to just stay the same policy. We can actually continue to learn in this new environment, where we initialize our Q function with the Q function in the training environment, and then fine-tune that neural network using the target data as well as some of the base data. And it turns out that if you actually use fine-tuning with less than 800 grasps, you can get to a success rate of 98% success in this new environment when the gripper has been offset by 10 centimeters. And so fine-tuning is actually a pretty viable strategy for adapting to changing environments, both for visual and physical changes to the environment. And we find that even after just 25 new grasps, we see strong improvements, and also kind of even better improvements as we continue to learn in the environment that we're in. So the takeaway here is that we can adapt to new environments. We can adapt to changing environments, in this case with an afternoon's worth of data, by just continuing to learn, continuing to collect data and update our models using that data. Now, this is kind of one baseline approach that I wanted to mention, but in the rest of this talk, we want to focus on, can we adapt faster? An afternoon might be kind of a long time to wait to have our robot adapt to a new environment. And so Annie and I will be talking about 3 different approaches that allow us to adapt much faster than that. First, we'll be talking about how we can use meta-learning to adapt in just a few time steps, in actually less than a second. Then Annie will be talking about how we can actually anticipate how the environment might change to actually adapt in advance of the change. And then finally, Annie will be talking about how we can actually influence how our environment changes to do even better. So now let's start by talking about kind of few-shot adaptation and how we can adapt with a small number of time steps. So in this part of the talk, we're going to be looking at a model-based reinforcement learning approach. And the way that this kind of base algorithm works is we collect some data, we fit a neural network dynamics model to that data to predict the next state given the current state in action. And then we use this learned model to plan actions using model predictive control, where we consider roll out a number of different features and optimize for the one that we think will optimize for the sequence of actions that will lead to the outcome that we want. And then we repeat this process, adding data that we collected with planning back to our data set so that we can continue to improve our model. Now, model-based RL is a nice framework for allowing agents to solve a number of different tasks. assuming that you can fit a good dynamics model to all of your data. However, there are situations where your dynamics might actually be changing, potentially even in real time. So for example, we might be considering a robot that is kind of traversing through its environment, where there might be changes in the terrain, or there might be a motor malfunction, and we want it to be able to adapt to each of these things that it encounters over the course of its experience. And so the way that we're going to view this problem is we'll kind of look at the robot's experience, and we want it to be able to adapt to a small amount of experience, for example, k time steps, so that it can actually use this most recent k time steps to produce a model that is accurate for the following time steps. And in particular, you can essentially view this problem of online adaptation as a few-shot learning problem, where we want to learn with a few or k data points of experience, such that we generalize well to the next number of time steps. And so that means that we can use a meta-learning approach to learn how to adapt with a small amount of data, where different tasks fed into the meta-learning algorithm correspond to these different temporal slices of experience. And so that's exactly what we're going to do. And so here's a kind of a schematic of this, where essentially we're going to store our recent history. In this case, we're considering k has changed to m. So we're looking at the last m time steps. We're then going to update our dynamics model using those last m time steps, using some update procedure. And then we're going to plan using our updated model that's hopefully updated to the most recent thing that has happened to our robot and can effectively model those situations. Now, a key question is, what does this update procedure correspond to? If you just run fine tuning and m is small, like say m is 8 time steps, you probably will either overfit or won't be able to effectively adapt to such a small amount of data. And so what we're going to do is we're going to meta train or learn how to adapt with only 8 time steps of experience, essentially learn this update procedure such that it generalizes and produces a model that can effectively predict the dynamics at the upcoming time steps. There's a number of different ways that you could perform this meta training. You can use recurrent models. You can also use the model agnostic meta learning algorithm. And this latter algorithm is what we found to be more effective. And so what does this look like? We considered a number of different dynamic environments. And first, we just ran kind of a baseline approach of just running model-based reinforcement learning. And what we found is in dynamics environments where, for example, a limb becomes crippled, or where the robot is kind of walking along these, kind of like a pier with these panels of different damping factors, model-based RL isn't able to learn an accurate model that can capture all of these different kinds of changes in the environment. Where in contrast, if we actually meta train for an update procedure and actually update with only 8 time steps of experience, which is actually online, it's so fast that you don't actually see it, we can actually effectively adapt to the dynamics that are changing in real time and actually get the robot to the end of the environment. And because this is a model-based approach, this means that we can actually apply this algorithm. This means this algorithm is super efficient. The meta training process itself requires many fewer samples than model-free approaches. And this means that we can actually run this algorithm on real robots. So we collected data from different terrains on this Velociroach robot. And the Velociroach robot is a kind of a really small robot with 6 legs. And it's actually a really great test bed for testing some of these algorithms because the dynamics change drastically as you change the condition that it's in. So we meta-trained with this data from different terrains and then evaluated how well the robot could adapt to new scenarios such as being on a slope, having a missing leg, a payload, or calibration errors. And what we found is if we kind of run our approach, it's able to effectively adapt its dynamics model in real time in order to kind of walk in a straight line. Whereas in contrast, model-based reinforcement learning without this sort of adaptation tends to veer off to the right because it is missing the front right leg. Okay, so the takeaways here is that meta learning essentially allows us to accelerate adaptation to go from an afternoon's worth of data to just a few time steps of data. And it allows us to adapt to these dynamics changes with just a few time steps. And also, as an aside, we can actually use similar techniques to not just quickly adapt to these dynamics changes, but also to quickly adapt from simulation to real and get a policy that can adapt to the real world much more effectively than the policies that we get with domain randomization. Great, so this is kind of this idea of really fast adaptation through meta learning. Now, what Annie's going to talk about next is, can we take this a step further and actually anticipate how the environment might change and actually adapt in advance?
Great. Okay, so I guess next I'll be talking about how robots can anticipate to changes in their environment. And specifically, we're interested in a subset of environments where these changes can actually be predicted. And so as an example, robots that roam outside should ideally be able to adapt to different weather conditions. But the way that weather changes is often predictable, and that's because they follow these seasonal patterns. And so one way to model this kind of non-stationarity is with this Markov decision process that has underlying parameters that vary over time. And so we call this model the dynamic parameter NDP. And formally, it's equipped with a set of task parameters, Z, that define the dynamics and the reward function. And you can think of these task parameters as physical parameters like the mass of a payload or direction of a wind force. And we assume that we do know when these task parameters change, but not necessarily what they are. And so for simplicity, we assume that these task parameters are shifting at the episode boundaries and that they shift stochastically. Cool. So now that we formulate the problem, the objective we propose to minimize comes from the RLS inference framework, and we outline the objective here. But what's interesting about this objective is that it decomposes into two very intuitive components. And the first one, underlined in blue, corresponds to variational inference in a sequential latent variable model, where the observations are essentially the agent's trajectories, and the latent variables are these hidden task parameters. And then the second component, underlined in green, corresponds to maximum entropy RL, where the policy is also conditioned on the inferred task parameters. And so together, this objective is essentially performing joint representation learning of the environment and reinforcement learning with this representation. And to actually optimize this objective, we propose our algorithm LILAC. And in LILAC, we're introducing this inference network that infers the task parameters given the trajectory, as well as this decoder network that reconstructs that trajectory. And since the prior P of Z prime given Z is unknown, we also try to learn that with a neural network on top of the representation. And so we built these components on top of the soft factor critic algorithm, which just takes in the task parameters from the inference network. And then when the agent has to act in the environment during a new episode, we'll first infer the latent task parameters from the previous episode. And with the learned prior, we can then predict the next set of parameters and pass that into our policy. And so to evaluate this algorithm, we designed some experiments, some environments that kind of exhibit this kind of non-stationarity we might find in more realistic settings. And so, for example, we might want a robot to be able to track a moving goal, or to move against different wind forces, or to carry different payloads. And overall, we see that LILAC can maintain more successful behavior in each of these environments. And unlike the other methods, LILAC is able to do this because it's proactively modeling the changing task parameters. Something else we wanted to investigate was whether LILAC could handle environments with different rates of non-stationarity. And so these bottom four lines in this plot represent the performance on these different rates. And we see that LILAC is pretty much performing the same across these different environments. And so its performance isn't really determined by the rate of the non-stationarity, as well as we see that in the stationary case where the target isn't moving at all, Lilac performs just as well as a standard reinforcement learning algorithm. And those are represented by the blue and the black dotted lines. And so the takeaway here is that in order to handle environments with persistent non-stationarity, we can often model and anticipate these changes, which then allows robots to instantaneously adapt to them. Also, since Lilac is modeling environment shifts separately from policy learning, its performance also doesn't change under these different rates of non-stationarity, which is a nice property. And so far we've looked at non-stationary settings where the robot's environment is evolving independently of the robot's actions. But settings that involve other robots or other people are also non-stationary. And from the perspective of the robot, these other agents are updating their behavior, and these updates are often in response to the robot's actions. And so we'll next show that we can actually apply a similar framework to Lilac that allows the robot to not only react to these changes, but even influence them. So prior work for handling these multi-agent interactions would explicitly model the low-level policy of the other agent. Instead, we think it can be more efficient to just maintain a high-level representation of the other agent's policy. And so we call this their latent strategy, but this latent strategy can essentially change across interactions between agents. And so similar to before, how we were learning a representation of the environment in Lilac, we'll try to learn a representation of the other agent's latent strategy in this multi-agent setting. And so we will encode an interaction and try to predict the next latent strategy of the other agents. Then by training a policy conditioned on this predicted latent strategy, the ego agent should then be able to react to the other agent. And we call this method learning and influencing latent intent, or LILI. And so we evaluate this framework in the simple navigation task where we have an ego agent in teal and the other agent is represented in gray. And the ego agent first starts each interaction at T1, while the other agent is somewhere along the shaded blue circle. And so the ego agent needs to capture the other agent in this game as quickly as possible, but doesn't get to observe the position of the other agent. And after each interaction, the other agent will be moving around the circle, which creates this non-stationary environment. And so in this visualization, the teal path is representing the trajectory taken by the ego agent, and the teal circle represents its final position. And so this first policy is trained with just soft actor critic, and we see that the agent is moving to the center of the circle at every interaction. And that's because not knowing where the other agent is, the ego agent receives essentially the highest reward at the center. And so in contrast to this, our method Lily can model the other agent's behavior a lot more successfully and capture the other agent. But notice that the other agent is being captured along this lower part of the circle, the red region. And if the goal is to reach the goal as quickly as possible, then ideally the other agent should be situated at the top of the circle. And essentially it should be influencing the other agent to move towards that blue region. And so instead of just reacting, what we actually want is a policy that can influence the other agent's strategy. And this influential behavior can actually be learned by maximizing the long-term rewards summed across interactions. And this objective will naturally motivate the ego agent to act in ways that lead to more desirable future strategies in the other agent. And so now returning to our navigation example, we see that the Lily agent with influence learns to trap the other agent at the top of the circle. Tested our approach in this air hockey game played between two robots. And the goal is to learn a policy for the ego agent to block shots from the other agent. And the other robot can strike the puck in one of three directions, and this corresponds to its three strategies. So it can aim either to the left, down the middle, or to the right. And after each trial, the other agent will select a new strategy based on the last interaction. And so the ego agent earns a reward if it successfully blocks the puck. And if it blocks the shot coming down its left side, it earns a bonus reward. And so this means that influencing the opponent to aim left will earn it higher long-term rewards. And so this first policy was trained with soft-touch critic, and we see that the agent only learns to block on the left side, on its left side. Oh, sorry, on its right side. But near the end of training, it does end up switching to, to blocking left instead. And as a reminder, blocking left will earn it higher reward. And next we see that Lily can block a lot more successfully than soft-touch critic. It doesn't always get that bonus reward for blocking left. Whereas Lily with influence, I don't know if it's clear through the videos right now, but Lily with influence can block, can manipulate the other agent to kind of alternate between the left and the middle shots. And if we were to look at this success rate only, we see that Lily with influence has similar blocking success as Lily without influence. But where we actually see a difference is when we look at how frequently the opponent is firing in each direction. And Lily with influence will lead its opponent to fire left the most often, which is 41% of the time, while without influence, this distribution is pretty much uniform. And so to summarize, in some non-stationary settings, this non-stationarity will depend on the agent's own actions, like it does in multi-agent interaction. And in these settings, we can anticipate and react to the other agent's behavior. But not only that, we can also learn to influence it across repeated interaction.
Yeah, and thank you everyone. I guess to kind of summarize the talk in full, we talked about kind of quickly adapting, also anticipating and adapting in advance, and then finally influencing how the environment changes. And we think that kind of all of these three kind of key ideas or themes can be useful, not just in the examples that we showed, but also in a variety of different algorithms and instantiated in different ways. And we look forward to the discussion.
So thank you very much for the really amazing talk. Like it was really interesting to see like this research, where unfortunately